Hello guys, welcome to the lecture 41 of deep learning series. In this video, we'll be discussing about stochastic gradient descent with momentum. Okay, now to understand this topic, we need to have a basic understanding of few prerequisites. Okay, these are our prerequisites. Now to understand these prerequisites, let us see small intuition. Okay, now let us say this is our neural network. Okay, which has some features. Let's say we have output y hat. Okay, let's say this is our neural network and this is our predicted output. Now for this predicted output, we'll be having a corresponding true output, right? Okay, now how will be relating this y and y hat? Okay, how will be relating this true output and predicted output? Through loss function. Okay, loss function of y comma y hat. Okay, now if you keenly observe, this y hat is this y hat is directly dependent on few of the parameters. Okay, that is weights and bias. Okay, this y hat is dependent on few parameters, that is weights and bias. So indirectly we can say that loss function is dependent on weights and bias. Okay, loss function is indirectly dependent on weights and bias. Okay, loss function is dependent on basically on the y hat, and our y hat is dependent on weights and bias. Okay, now by altering this weights and bias, we'll be able to calculate this predicted output. Okay, now when we keenly observe this, loss function is dependent on weights and bias. Now we'll be coming to our first graph, that is two-dimensional plot. Okay, here if we see, our loss is dependent on only single parameter, means we have a neural network this way. Okay, which has only weight. Okay, which has an input feature which has only single weight, and we'll be having corresponding output. Okay, this is the two-dimensional plot where we'll be altering this w value to minimize this loss value. Okay, we'll be altering this w value to change this value of loss. Okay, to allow loss to reach to its global minimum. Okay, this is the optimized weight value. Okay, this is the optimized weight value when it comes to a two-dimensional plot. Now we'll be coming to a three-dimensional plot where we'll be having a single weight and single bias. Okay, we'll be having the same diagram but added with bias. Okay, we'll be having the same diagram but added with bias. Here if we see, we have a weight and we have a bias. Now we need to tune both this weights and bias value. Okay, weight and bias value, to minimize this loss. Okay, but understanding the loss in this case is very much easy because it is a two-dimensional plot. Okay, in two-dimensional plot we can see that this is our global minimum point. Okay, in two-dimensional plot, in any two-dimensional plot, we can easily determine the global minimum point, but it is hard to visualize the global minimum point on a three-dimensional plot. Okay, now if you keenly observe this graph, okay, if you keenly observe this graph, it is difficult to determine where the global minimum point is. Okay, I have randomly taken some global minimum point to make you understand. Okay, let us say this is our global minimum point. Okay, now we need to alter this weights and bias. Okay, we need to tune this weights and bias to minimize this loss to reach this global minimum. Okay, to make loss reach this global minima, we need to alter this weights and bias values. Okay, this is in case of three-dimensional plot. Now when it comes to a contour plot, this contour plot is the representation of an higher dimensional graph. Okay, now let us take an example of this three-dimensional plot. Okay, now this three-dimensional plot is, okay, this three-dimensional plot is scattered. Okay, like we can say that it is reduced. Okay, this reduced dimensionality. Okay, this three-dimensional plot is represented as two-dimensional plot on a contour plot. Okay, the same three-dimensional plot is reduced to two-dimensional plot, and the two-dimensional plot becomes a contour plot. Okay, now let us say we have n-dimensional plots which get reduced to two-dimensional plot to represent a contour plot. Okay, this contour plot is the reduced dimensionality of an n-dimensional plot. Okay, if we have n number of parameters, okay, if we have n number of parameters, we can like project. Okay, we can project them onto a two-dimensional plot and we'll be getting a contour plot. Okay, now understanding this contour plot is very much easy. Okay, now let us say we have started from here. This is a point A. Now let us say this is the projection of, okay, this contour plot is a projection of this three-dimensional plot. Okay, now let us say we have started from here. Okay, same point, same point. Now gradually we reach this global minimum point, but in a contour plot we can see that easily we can memorize, okay, easily we can observe how our point A is reaching the global minima point B. Okay, this contour plot makes visualization more easy. Okay, higher dimensional plots are represented as lower dimensional plots in a contour plot. Okay, this contour plot helps in easy visualization of higher dimensional plots. Okay, it helps in easily understanding of weights and bias. Okay, variations in weights and bias values. Okay, these are all the three plots that we basically encounter in deep learning. Okay, there are many other plots, but these are the basic plots that we encounter in deep learning. Okay, now from the next section we'll be diving into a topic that is stochastic gradient descent with momentum. Now let us discuss two types of graphs that we basically encounter in deep learning. Okay, this is the graph. Okay, this is the convex graph that we basically use as reference. Okay, this graph is basically used as reference to explain any optimization algorithm like gradient descent. Okay, this is just an reference. Okay, this is just an reference graph. Okay, in real world scenarios the graph is actually in this way with multiple obstacles. Okay, you can see that this is our first obstacle, this is our second obstacle, and this is our third obstacle. Okay, the graph will not be very much smooth. Okay, it will be having some disturbances. Okay, so this is non-convex, so this is convex. Okay, in real world scenarios we'll be basically encountering this kind of graphs. Okay, now to explain this concept of convex and non-convex graphs I'm using only single weight. Okay, because it will be easier to visualize, so that is why I'm using only single bit. Okay, now first let's talk about a convex graph. Okay, now let's say a gradient descent has started its weight updation from here or here. Okay, now to reach this point it reaches without any difficulty. You can see that there is just a linear path to reach this global minima point. Okay, to reach this global minima point it can take some linear steps and can converge over here so that we can get some optimized weight value. Okay, this is with respect to a convex graph. Now the difficulty comes with a non-convex graph. Okay, in a non-convex graph we'll be having three problems. Okay, first is local minima, second is saddle point, and the third problem is higher curvature. Okay, we'll be explaining, okay, I'll be explaining these 3 points in detail. Okay, first problem is local minimum. Okay, now with respect to this graph we have a single local minimum, but when we have an n-dimensional graph, okay, when we have basically n parameters we'll be having n local minimas. Okay, we'll be having multiple local minimas. Okay, but in our graph for simplicity we have taken only single local minima. Okay, now when we take this as a local minima, now let's say our gradient descent has started its weight updation from here. Okay, it started the weight updation from here. Now it basically updates this way. Okay, it takes multiple jumps and finally reaches this point. Okay, after reaching this point our gradient descent will think this as a global minimum. Okay, why it thinks this as a global minimum? Because when you compare the slope over here, okay, when you see the slope over here you'll be having dou L by dou W equal to 0. Okay, the slope at this point is equal to 0. Okay, and the slope at this point is also equal to 0. So they're comparable, right? They're comparable. Okay, local minima is nearly like a global minima, right? So a gradient descent will understand, okay, we'll assume this as a global minima and will stop updating the weights. Okay, our gradient descent will think this has a global minima and will stop updating the weights because dou L by dou W is equal to 0. As it is equal to 0, our old weight value and new weight value will be equal. Okay, they will be equal. So this is our first problem, that is local minima. Okay, now when we talk about the second problem, that is saddle point. Now when it comes to saddle point we'll be having the graph in this way. Okay, it may be an horizontal line or it may be some raising curve. Okay, not much raising curve but a little raising curve. Okay, this is a horizontal line or it may be like little raising curve. Okay, it may also be in this way. Okay, slightly tilted. Okay, this is slightly up tilt, this is slightly down tilt. Now due to this what happens is here the slope will be equal to 0 because the slope of a horizontal line is equal to 0. Okay, the slope of a horizontal line is equal to 0. So due to this old weight value will be equal to new weight value. Okay, this is a point of saddle point. Okay, this is basically saddle point. Now when it comes to this case it will be nearly equal to 0. Okay, the slope will be not exactly equal to 0 but nearly equal to 0. Okay, sorry, it will be nearly equal to 0. Now when it is nearly equal to 0, the training becomes much slower. Okay, the weights will be updated much slower. Okay, the training becomes much slower and weights will be updated much slower. Due to this, training time increases. Due to this, training time increases. Okay, similar in this case as well. Okay, when it is down tilt, we will be also having the slope value nearly equal to 0. Okay, in this case, the weight ablation will be stopped and training also will be stopped. Okay, when it is on perfect horizontal line, the train will be stopped. And when it is on raising, okay, little raising, okay, not much raising, but a little raising curve will be having nearly equal to 0 slope. And when it is also slightly down tilt, will be having nearly equal to 0. Okay, so due to this, training time basically increases. Okay, this is a problem of saddle point. Okay, now we'll be seeing the third problem, that is higher curvature. Now, to understand this higher curvature, we'll be seeing a small example. Now, tell me, among this first circle and second circle, what do you think has a higher curvature? Okay, this second circle, right? Okay, when you observe this second circle, it has higher curvature, right? It has a higher curvature. Okay, the curve is slightly higher. Okay, it's much more like curvy. It's much more curvy. Okay, than the first curve. Now, let us say a gradient descent has started from this point, and in our second case, it has started from this point. Okay, now by taking the slight jumps, it basically need to reach this point, that is global minimum. Okay, this is our global minimum point. Okay, now as it is much more curvy, we'll be seeing an overshooting problem. Okay, it may jump off from here. Okay, it nearly reaches this global minimum point much faster. Okay, it is because it is higher curvature. Okay, it's having higher curvature, it reaches this point much more faster. Okay, now think it like a car. Now let's say car has started from here. Okay, now when the car started from here, as it is much more curvy. Okay, like let's say this is our hill. Okay, let's say this is our global minimum point. Okay, car started from here. Okay, it need to reach this point. Now when it started from here, it takes longer jumps. Okay, it takes longer jumps, means it has more acceleration. Okay, more velocity towards this point. So due to this, what happens is it may overshoot to here. Okay, due to this, it may overshoot to here, and again it may reach over here. Again it may overshoot to this point. Okay, again it may overshoot to this point and slowly reaches to this point. Okay, this is the problem of higher curvature. Due to higher curvature, we'll be having more velocity. Okay, more faster weight ablation, and due to this, it may overshoot. Okay, it may overshoot and oscillate at this point. Okay, oscillate at this global minimum point. Okay, now after oscillating, it slightly reaches to this global minimum point. Okay, it slowly reaches to this global minimum point. Okay, now due to this oscillation, our training time is basically increasing. Okay, due to this oscillation, the training time is basically increasing. Now let us take a second scenario where the car started from here. Okay, this time the hill is in this way. Okay, two hills are in this way. Now when the car started from here to reach this point, it may take some larger steps, but there will be slight overshooting over here. Okay, more than this. Okay, more, sorry, we'll be having less overshooting over here and more overshooting over here. Okay, the acceleration over here will be much slower than the acceleration over here. Okay, the the velocity is much higher than this. Okay, so when the curvature is higher, we'll be having less slower. Okay, like less faster weight ablation. Okay, when the curvature is slightly higher. Okay, when the curvature is slightly higher, okay, like less bulge, we'll be having less faster weight ablation. So due to this, this oscillating problem will be solved. Okay, due to this oscillating problem will be solved, and training time becomes much optimized. Okay, training time becomes much optimized. So these are the three problems that we face in a non-convex curve. Okay, in a non-convex graph, we'll be facing first local minima, and second saddle point, and third global minima. Okay, now in the next section, we'll be understanding why we have actually discussed this convex and non-convex curves. Okay, we have set a perfect base to understand the concept of momentum. Okay, this concept of momentum solves the problem of non-convex graphs. Okay, we have seen three various problems in a non-convex graph. First is that is local point, second is saddle point, and third is higher curvature. Okay, these three problems, and additionally these two problems are solved with the help of concept of momentum. Okay, we have already discussed about those three problems in detail. Now let's see what actually these two problems are. Okay, first is consistent gradient. Okay, let's say this is the weight versus loss graph. Okay, now this is a global minima and a gradient update and start from this point. Okay, now in a consistent gradient problem, what we do is we update the weights. Okay, we update the weights in a consistent way. Okay, in the same fraction. Okay, now basically what is our aim? Okay, what is our aim for faster updation? We basically start with higher steps. Okay, we basically start with higher steps, and eventually nearing to this global minimum point, we decrease the step size. Okay, we decrease the step size. Okay, first we start with larger steps, and eventually after reaching, okay, after nearing this global minimum point, we reduce the step size. Okay, but in consistent gradient, we'll be having the same step size. Okay, we'll be updating with the same step size. Okay, now due to this, the training time increases, and uh, the training will be much slower. Okay, the training will be much slower. Okay, but this is the optimized way. Okay, this is the first problem of consistent gradients, and second is noisy gradients. In noisy gradients, we basically will be having some noisy gradients. Okay, some irregular gradients which may tend to the problem of overshooting. Okay, in this way we may have gradients like rolling over here and there. Okay, this is the problem of noisy gradients. Okay, now let us see how these two problems are solved with the help of concept of momentum. Okay, now let's take a small analogy. Let's say this is point A, point B, point C, and our destination D. Okay, our car has started from this point. Okay, our car has started from this point. Okay, now let's say this point is LB Nagar and this point is Miapur. Okay, now let's say we're starting at LB Nagar and our destination is Miapur. Okay, now let's say we are starting and we are asking the person A, I'm like the path I'm going is right or wrong. Okay, you ask person A, is the path I'm going is right or wrong? If the person A says it's right, then you move much faster. Okay, then the initial speed you move much faster because you're confident about the direction. Okay, now again you ask the person B, is the path I'm going right or wrong? Okay, if he say it is right, then you go in a much confident way. Okay, now again you ask the person at point C, if he also tells it is yes, then you move in much faster and reach this point D with less, okay, with more speed and less time. Okay, you reach from this point to this point with larger speed and less time. Okay, this is basically the concept of momentum. Okay, in concept of momentum, you verify the previous gradients confident and move to this global minimum point. Okay, you verify the confidence of gradients of previous. Okay, you basically verify the confidence of previous gradients. Okay, after verifying the confidence of previous gradients, if the in verification, okay, in verification, if the gradients are updating in right direction, okay, you think that if the gradients are updating in right direction, then you move much faster. Okay, to reach from this point to this point, first you eventually take smaller steps and again you verify is the direction I'm moving, okay, is the direction I'm moving is right or wrong. Okay, if you verify it as right, you move much faster. Okay, in the same direction you move much faster. Okay, this is basically how momentum works. Okay, this is the concept of momentum. Okay, now what is the advantage of this concept of momentum? Okay, it solves all these 5 problems and also it is faster than normal SGD. Sorry, normal SGD. Okay, normal SGD takes, let's say, 5 seconds for training. The SGD with momentum may take let's say 2.5 seconds. Okay, half the training time. Okay, the normal SGD is much slower than the SGD with momentum. Okay, sorry, this is SGD with momentum. Okay, SGD with momentum is faster than the normal SGD because you are verifying the previous gradients. Okay, you are verifying the confidence of the previous gradients, and you are moving in a particular direction in a faster way. Okay, this is the concept of momentum, and we'll be seeing the mathematics behind this concept of momentum. Now let us discuss the mathematics behind the concept of momentum. Okay, these two are the formulas that are responsible for the mathematics behind the concept of momentum. Okay, among them the first formula is Wt plus 1 is equal to Wt minus Vt. Okay, it is much comparable to our weight updation formula, that is W nu is equal to W old minus learning rate dou L by dou W old. Okay, you can see that it is much comparable to this formula. Okay, the only change we have is around at this term. Okay, in place of this term we are having Vt. Okay, this Vt is nothing but the velocity at time step t. Okay, this is the velocity at time t. Okay, as we are talking about the speed, okay, in concept of momentum we are talking about the concept of speed. So our velocity is involved. Okay, the velocity is involved. Okay, this Vt is nothing but velocity at time t. Okay, now this Vt can be further expanded as beta into Vt minus 1, that is previous velocities. Okay, that is previous velocities plus learning rate delta Wt. Okay, this delta Wt is same as this. Okay, this slope value. Okay, this gradient value. Okay, this delta Wt is same as this gradient value. Okay, now the only extra term that we have is this part, right? This is the extra part we have in this entire formula. Okay, this part is called momentum. This part is referred as momentum. Okay, in this momentum, okay, in this momentum we have two terms, that is beta and Vt minus 1. Okay, this beta is referred as decaying factor. Okay, if you want to understand how this term, okay, how this term has evolved, please refer to my previous video on exponential weighted moving average. Okay, I have explained this concept in detail. Okay, this beta is decaying factor which is from 0 to 1. Okay, this beta is from 0 to 1. Okay, now I'm telling that this part is responsible for the momentum. Okay, how it is responsible for momentum. Okay, now let's say we have beta value as 0.9. Okay, we basically calculate 1 by 1 minus 0.9 and this comes out to be 10. Okay, this comes out to be 10. Okay, now this 10 value represents, we are considering, okay, in calculating this Vt minus 1. Okay, in calculating this Vt minus 1 we are considering previous 10 velocities. Okay, in calculating this Vt minus 1 velocity we are considering previous 10 velocities. Okay, we are considering previous 10 velocities. Now let's say we have beta value is equal to 0.2. We'll be having 1 by 1 minus 0.2, we'll be having 1 by 0.8, we'll be having something around 1 point. Okay, something around 1 point. Okay, now in calculating this Vt minus 1 velocity, okay, velocity at time t minus 1, we are using our previous velocity. Okay, we are using our previous velocity. Okay, just previous velocity, but in this case we are using previous 10 velocities. Okay, you can see that the concept of momentum is clearly involved. What I have told in the concept of momentum, we use previous gradients, right? Okay, we use previous gradient and we verify the direction and we increase the velocity. Okay, you can see that we are using previous velocities. Okay, previous velocities, and we are verifying the direction and we are increasing the speed. Okay, we are increasing the speed over here. Okay, this is basically the concept of momentum. Okay, this is basically the mathematics of momentum. Okay, now this beta value, if it is equal to 0, okay, we'll be seeing the effect of beta value. Okay, if this beta value is equal to 0, we see that it acts as, okay, this formula acts as normal SGD. Okay, if beta value is equal to 0, it acts as normal SGD. Okay, and remember this beta value can't be equal to 1. Okay, beta value should always be between 0 to 1, but not exact 0 or not exact 1. Okay, the beta value should not be exact 0 or should not be exact 1. Okay, when it is exact 1, then no decaying is applied. Okay, no decaying is applied. Okay, so when it is equal to 0, we see that it is a normal SGD, no momentum. But when beta value is equal to 0, we see no decaying. Okay, we see no decaying. Okay, remember this part is our momentum part. Okay, this part is our momentum part. Okay, this is the entire mathematics behind the SGD with momentum. Okay, to understand what this term is, please refer to my previous video on exponential weighted moving average. Now, with the help of contour plots, we'll be understanding the advantage of SGD with momentum. Let's say this point is referred as global minimum. Okay, this point is global minimum. Now let us say we have started from this point. Okay, now in normal SGD you take smaller updates. Okay, you take the updates in this way and finally reach to this point. Okay, the updates are in this way, but in SGD with momentum you take smaller steps. Okay, you take like much higher steps. Okay, you take much higher steps to reach this global minimum point, because you're verifying the previous gradients. Okay, and if they till the direction is right, you're just increasing the speed. Okay, you're just increasing the speed. Okay, this is how SGD with momentum works. This is normal SGD. This is SGD with momentum. Okay, this is SGD with momentum, right? This is SGD with momentum and this is normal SGD. Okay, here you take much bigger steps. Okay, if you're confident, you take much bigger steps, so you'll be reaching to this global minimum point much faster. Okay, you will be reaching to this global minimum point much faster than in normal SGD. Okay, this SGD with momentum solves all the 5 problems with the non-convex graphs, and also increases the speed and decreases the training time. Okay, training time. So remember, the SGD with momentum is faster than normal SGD. Okay, this is the entire mathematics behind SGD with momentum. Okay, now there is a small concept that is left behind, that is the disadvantage. Okay, let's say the cons behind, let's say the cons with the SGD with momentum. Okay, there is single problem with this SGD with momentum, that is the problem of oscillation. Okay, we only have the single problem, that is the problem of oscillation. Okay, now in SGD with momentum, as you move with increased velocity, as you move with faster velocity, there's a chance that it may oscillate. Okay, there's a chance that it may overshoot over here. Okay, now let's say you're very much close to this global minimum point. Now after reaching, okay, after getting closer to this global minimum point, what happens is you may overshoot. Okay, you may overshoot in other direction because the velocity is high. Okay, as the velocity is high, you may overshoot in other direction. Okay, now again, as you verify with the previous gradients, again you move over here. Okay, again you move over here, again you move over here. In this way you oscillate but finally reach the global minimum point. Okay, you may oscillate but finally reach the global minimum point. Okay, now this is basically the problem of oscillation. Okay, here you are reaching but eventually you are oscillating due to higher velocity. Okay, this may increase the training time. Okay, this may increase the training time but to a lesser extent. Okay, it may not increase the training time much far higher, because you're finally reaching the global minimum point. Okay, you're finally reaching the global minimum point, but you're just oscillating at the global minimum. Okay, this is basically the concept of SGD with momentum. Okay, hope you guys like this video. If you have any doubts, please don't hesitate to comment in the comment section. Okay, if you like the video, please like, share and subscribe.